Okay, this is going to be a recording for the Chapter 17 Electrical Theory for CMCET 331 Electrical Systems. So let's go ahead and get started here. So first off, we have to discuss what is electricity. Well, for us, electricity is a form of energy tied to the existence of electrical charge, and it is actually linked to magnetism. Now, this is kind of a simplified version as compared to what you would get in your physics class, but for us, this covers the basis of what we need to have in our course. So we do see that electricity does play a fundamental role in everything that we work in. Basically, all of our modern tech utilizes it in some way, either in its actual use or in the manufacturing of it. So there's two general ways that we can talk about electrical theory. One deals with the more modern theory where we talk about electron clouds around atoms and things like that. The easier one is to discuss it in terms of classical theory, where you can see here I have an example where we've got three copper atoms lined up. In that center nucleus, we've got our protons and our neutrons. And then on the outside, we've got our electron shells, so our different rings that are out there. And one of the things that makes a good material for conducting electricity is having just a very few amount of electrons on that outer edge. We call those valence electrons. So that outer electron, you can see it there on the copper atom where the blue arrow is starting to point to it. It's easy for us to be able to kick that off onto the next atom of copper, and then it can just keep going down, just kind of traveling down the line as we go. And so that's basically what we're doing, is just kicking electron down the line of all these. And basically, as you kick one onto the next atom, it's kicking its extra one onto the next, it's kicking its extra one onto the next. And so it's kind of a chain reaction the way it works, similar to how if we played with like a Newton's cradle, the swinging balls that knock each other. Okay. Next thing we'll talk about is we'll talk about current. Now, current is the actual flow of electric charge through a conductor. So this is the exact wording you're going to need to remember on the test, quizzes, and homeworks now. So one thing we need to consider is exactly how fast is electricity? Well, one electron on its own moving atom to atom is only moving half an inch per second, or about 150 feet per hour. But when remember we talked about how electricity actually is a chain reaction down a line of atoms. So therefore, in that chain reaction, we're actually moving about 186,000 miles per second, which is about 300,000 meters per second. So roughly, we're talking about the speed of light here. Okay. So let's see. Next up, we have our what are the different ways that we classify our materials. We've got three main categories: conductors, insulators, and semiconductors. Now, conductors are materials that carry electrical current very easily with little resistance to that actual current flow. Examples of this might be copper, aluminum, gold, and silver. Insulators are materials we use to help resist the flow of electrical current. So examples of this might be certain types of plastics, rubber, also glass and ceramics. The third main category we have are called semiconductors. Now, these are neither good insulators or good conductors. They will conduct electricity, but typically we lose a lot of the energy through them in the form of heat. So our bodies are great examples of this. We can conduct electricity, but a lot of that energy is dissipated into us, typically in a not so great way. Superconductors are another material category out there we can talk about. At standard room temperatures, they act almost like insulators, not isolators. But when we supercool them, say in liquid helium, liquid oxygen, liquid nitrogen, liquid hydrogen, where all of the structure of the atoms in those materials actually line up just perfectly, and they become almost 100% efficient conductors. Let's see, current flow. We talked about what is current. So current flow is electricity is the flow of current through a conductor. So that's another way to make that statement. But we have to figure out in what way are we going to actually induce current flow to work. So there's different ways we can actually force the flow of current through a material. First is we can do static electricity. We do that by friction. Thermoelectricity through temperature. We can also do piezoelectricity. Piezoelectricity is we actually deform or change the shape of something and then it lights up. Electrochemistry, we can use a chemical process. Photoelectric is lights. So we can actually use whether a lighter is on or off to actually cause current to flow. We can also use magnets to help generate electricity, and that's kind of where we do a lot of them. There's my little joke about magneto, isn't that nice? And then also we can have the alternative, this is just a joke one, but the idea of using Pikachus on a treadmill to make Pokemontricity. Units of electricity, these are the three first terms that we have to worry about now. First off is voltage. That deals with, think of it in terms of like the electrical pressure. This is what's actually providing force to move the current down the line. Our units are volts. Our letter designators are E or V, and typically that E will look kind of like a backwards 3. It's actually an epsilon symbol. Our analogy for this is we think about water pressure or gravity on water pressure in a pipe system or gravity on an open stream helping move the water. Current, this is the actual flow of electrons. The units there are amperes or amps. Letter designator for this is an I. Our analogy for this is we look at it like it's flowing water. So this is the actual flow of water through a system, like the flow of electricity through a conductor. At the bottom down here we have resistance. That's our opposition to current flow. Its units are ohms, or we use the omega symbol also. Letter designator for that is R. And the analogy for this would be like a pipe restriction in a closed pipe system, or we could think about it like rocks in an open stream causing rapids. And we think of that turbulence as how we lose energy in that system. Okay, our first law that we have to do, here's where the math comes in. So first off here we have voltage, which we talked about. We have amperage, and we have resistance. So if we want to think about voltage is the E, amperage is the I, resistance is the R. Voltage equals amperage times resistance. So I've got a little example here. We've got basically a little battery, some wire, and a resistor of some type. Maybe it's a heating element, maybe it's a light, maybe it's some type of display, who knows. But I've got some data in here. So the source provides 12 volts. The resistance of whatever is using power is 6 ohms. And we know that there are 2 amps of current in the system. So if we think about it, if we took the 2 amps of current we measure in the wire, multiply that by the 6 ohms of resistance of the whatever's using our power, that'll give us 12 volts. It tells us what size of battery is running this system, or consequently, we can know that the system is 12 volts on the power source. We know our piece of equipment on the other side uses 6 ohms. We could take 12 divided by 6. That would give us 2 amps. And we can actually size our wiring based upon that. And that's going to become very important because we're going to be getting into that later on. Okay? So let's talk about power now. So we talked about current, voltage, and resistance. Let's talk about power now. So power is the rate at which work is accomplished. It's work or energy released divided by time. The most common unit for how we see this in our daily lives is through horsepower. Motors are typically rated in this. To give you an idea here, 1 horsepower equals 33,000 foot-pounds per minute. So if you want to think about that in something kind of an applied fashion, that'd be the equivalent to lifting a 1-ton weight at a rate of 6.5 feet per minute. So that's some serious weightlifting going on right there. Kind of understand why we use horses for this. 1 horsepower, to convert over into our electrical terms, is going to be 746 watts. Okay, and watts is what we measure electrical power in. All right. Joule's law, this is our second law we're going to use for being able to do our math. And in this one, power in watts equals voltage in volts times amperage in amps. Okay, so here's a little example here. We've got power we need to solve for. We know that our voltage equals 12 and our current equals 2. So to solve for power, we just need to multiply those together, and that would tell us that this is 24 watts. So as an example is, you've got wire sized for 2 amps, you've got a 12 volt source, so therefore you know that you could run a 24 watt light bulb. Energy usage. Okay, this is going to be kind of split between a couple places in these slides. Let's talk about it first. So energy usage is power used by an appliance that we then multiply by the length of time we use. So we know that we measure power in watts. To actually be able to be billed for it, we actually have to have an actual time unit here. So we multiply Simply, how much power do we use by how much time has it been used over? So one of the things that you're going to see here, though, that if we ever look on one of our um, power meters, the electrical meter that's on the side of the house, you'll notice that it's listed in kWh. Now that's kilowatt hours. So that's 1,000 watt hours. Now that might seem like, well, that's kind of extreme, but when we get into our actual power usage, you're going to see why that's important. Okay, so here's another example of it going through. We use Q in our equation. So Q is equal to the power that we spend, that's in watts, just multiplied by the amount of time. So as an example, if we used a 6-watt string of light bulbs for 4 hours, it'd be 24 watt hours or 0.024 kilowatt hours. All right, let's talk about our circuits now for a minute, and then we're going to come back to our power usage over time and billing. So electrical current, to have an electrical circuit, we have to have a continuous path along which an electric current can actually flow. So as an example, a simple circuit has 4 main parts. There's a power source, like a battery or a generator. There's a load. This is the component that actually consumes energy, simple like a lamp or a toaster. And then we have conductors. These actually carry the current. Most common material we use are wires. And then we have a switch. The switch actually allows our circuit to be open or closed. So if you look at these pictures right here, you'll see on the left we do actually have a circuit here, but we actually have no way to control that light unless we actually disconnect one of the wires, either from the lamp or from the battery. Now that could be kind of dangerous for us. The one next to it, we can see here they've shut off the light because they've actually broken the wire. But to give us control over the system, on the third one, they've actually installed a switch. This allows us to manually open and close this switch for how we're going to look at it. Now let's talk about those terms real quick. A closed circuit, this allows us to keep current flowing in an electrical conductor, meaning we have to have a fully closed circuit, a full loop for how things go around, from the source to the usage equipment, all the way back to the source. So that's a closed circuit. It's an uninterrupted path that allows for current flow. Then we can also have an open circuit. So if you look back, that would be the middle picture here. Then the closed circuit is the one on the left. All right. So an open circuit is any time where we've actually broken the circuit open, might be by a broken wire, might actually be by a switch. And that allows us to actually deactivate the circuit and not have power running through it. Lastly, we could have what's called a short circuit. This is when you have an inadvertent shortcut develops in a circuit and allows current flow to go. Meaning, as an example, if we look right here, if I had an arc of electricity between these 2 points, then that would actually be a short circuit. Or kind of an old movie back from the 80s. All right, types of circuits, there's two general ones that we talk about. First are series, then is parallel. Now, in any set of wiring we have what's called a hot conductor and a neutral conductor. The hot conductor carries current out to whatever is using the electricity. The neutral is our return path back to the source. So in a series type system, the power has to run through whatever, our example here is a light, has to run into the first light, then into the second light, then into the third, the fourth, the fifth, and then it can run all the way back to the source. Now the problem here is that if one of those lights goes out, the entire string is gone, kind of like an old set of Christmas lights. The second one is parallel. Now in parallel, we actually bridge across the hot and the neutral so that as we go down the line, none of the lights are actually in series anymore. So therefore, if the first light goes out now, the other lights are not affected. Now I will tell you though, while this seems like great, there is a difference in how power is utilized in series versus parallel. All right. So let's talk about those circuits for just a second again. So within those circuits, we have some different laws we're going to use, and these are by Kirchhoff. Excuse me. So the first one is, and when we talk about this, we're talking about in series. So first off, we know that the sum of the voltages is equal to 0, meaning that if I add up the voltage across any set of utilization equipment, maybe there's one here, and one here, this plus this will equal the voltage here at the source. The other one states that current is constant. So if I measure current on this side of the equipment and on this side, that current is going to be equal to each other. All right. So let's get into now how we can actually generate electricity. So first off is here we have magnetism. Now, magnetism is the force of attraction between ferromagnetic metals. Examples being like iron, nickel, cobalt, things that we can actually magnetize, okay? You can have naturally occurring magnets out in the environment, magnetite, and it looks like my slide cut off here, but I had like neodymium. We've heard of rare earth magnets before. Or we can actually create an electromagnet. This is where we take like an iron core, we actually wrap a wire all the way around it. If we induce current across these wires, so imagine I put a battery right here, that current flowing around that iron core will actually magnetize that core. Now, if we want to actually use the magnetic field to induce current, what we could do here, this is one of those old horseshoe magnets. We kind of remember those. Sorry guys, a little tired today. If we took this copper rod or iron rod, whatever we want to use, and we actually put it through, well, copper, not iron, don't use iron for this. But if we pushed it through this electromagnetic field, sorry, this magnetic field, in one direction, it would actually induce current only in one direction. If we raised it back up through in the opposite direction, current will flow in the opposite direction. So this is going to lead us into what we're going to call DC and AC current, because those are the two ways we can actually generate electricity. In DC, we are continuously moving only in one direction down, so kind of like this all the way down through our field. In alternating current, we're kind of moving back and forth in how we do it. Okay. Now, DC current, this it flows in only one direction through a circuit. This is basically from negative to positive. This is basically a battery. DC we typically only utilize in batteries now. And you can see how when we turn it on, the voltage comes up and then just levels out, and it gives us a nice steady voltage all the way through. Examples of where we use this might be things like flashlights, automobiles, your laptops use a DC battery, same with your tablets, your smartphones, your smartwatches, whatever. Mostly mobile equipment. The opposite side of that coin is alternating current. And this, if you look at the drawing on the right, you can see it's a sine wave. You might have remembered this back from your math classes, but it's a continuous reversal of the direction of current flow. So imagine we're constantly alternating the flow of current, kind of like we're putting a wave in a line. The disadvantage here is the fact that we're not ever going to get the full value of these peaks. We'll talk about that in just a minute. So alternating current, how do we produce it actually? Well, instead of having the magnets be side by side, we put them on opposite ends. We've got a little, kind of like a loop of copper here that we can spin. Now, when it's out of line with the magnets, you can see it produces 0. When it's in line with A on the left, B on the right, we get a positive peak. Spins a little more, out of alignment, we get 0 again at C. Flips to the opposite from up here. So here at D, now we're at negative voltage. And then when we get then up here at E, we're out of a line, we're back at 0, and then the cycle just repeats. So you can see E and A are the exact same. Single and three-phase power. To put this very simply, the difference is that instead of having one magnet generating a field for how we do our takeoffs, we actually take off at 3 different points. Basically, I think if you broke a circle into 3 portions, they'd be 120 degrees out of phase with each other. So basically, each one of them takes a third of the cycle as we produce that power. When we do this, we typically use 3-phase power when we're talking about larger equipment with heavier power requirements. Now, one of the cool things we can do with alternating current is the fact that we can use transformers that actually manipulate the voltage and the current. The voltage and current are directly related to each other inversely, meaning that if I drop the voltage, I can increase the current, or if I increase the voltage, I can drop the current down. This is what allows us to transport alternating current electricity over extremely long distances. And you've probably seen these before. This is a transformer for a buried electrical line. You might have seen this in the back of your yard. These are examples of the ones you might have seen up on a telephone pole. And here's an example from like an electrical substation. Now, the way that we actually figure this out is that it's the ratio of the number of coils on the primary to the number of coils on the secondary. And if you look in your book, there's a couple examples on how to do the math for that, but that's something I'll also go over in class for you. Inductors. Inductors are simply a coil of wire creating an electromagnetic field. If you remember, that was that coil of wire that was wrapped around the iron core to create an electromagnet. Capacitors, these are basically just batteries for how they work. But we take metal plates separated by air or some other material, and we're actually storing an electrical charge in that field between those two plates. Power factor we're going to talk about just for a second because we're going to get back into those peaks on the AC current. So in AC and DC circuits, they actually perform a little bit differently. In DC, we have a direct, remember that nice flat line, so we can say that voltage times amperage equals watts, okay? But when we get into an AC circuit, it's not exactly the same. So therefore, remember, we're not going to get that top, so we don't exactly get it. So we typically refer to those in terms of volt amps. Now for our class, this will be completely interchangeable, but I do need to cover this for you once. So here's kind of an example. We've all gone to the store and bought a bag of chips before. So the three parts of this are the real power, reactive power, and apparent power. So if we look at this bag of chips, the apparent power is the entire bag. We think, oh, I'm getting this entire bag of chips. It's all the way full, okay? However, once we open the bag, we see that only about 2/3 of it actually has chips. The rest of it is just full of air. Well, the chips inside are the real or true power, and that's always less than the apparent power. The reactive power is all of that air that's just up here. So if you want to think about power factor, it's real power over apparent power. So in terms of so if you want to think about that like a percentage, it's always less than 100%. Or if you want to think about it as a number, it'd be 1.0 would be perfect. We rarely ever see anything get all the way up to a 1.0. There are ways to help improve it, but having a low power factor actually can hurt you because it means you're utilizing a lot of excess energy to do the work that you're doing. There are different ways to overcome this. We can attach batteries to motors to help kickstart them. You might have seen this in some of the things that you work with. Some types of cars have these, sometimes different motors, maybe like an elevator motor have these. That way it's a nice smooth flow. One of the main advantages of doing power factor corrections in terms of how we bill is the fact that high power factors, meaning getting closer to a 1.0 or 100%, these help lower the amount of energy you're using to do the same amount of work. It also means that you're doing less, your equipment isn't straining as hard, it's not generating as much heat. If you do have low power factors on your equipment, it is possible the utility company could actually bill you at a higher rate than they would a company with a much higher power factor. Okay. Okay, kind of roundabout to back what we talked about before. How do utility companies actually bill us? So we figured out that we know Q, which is our electrical consumption. So now we just have to apply a cost to that. Well, Q is in forms of kilowatt hours. So therefore we just need to multiply it by dollars per kilowatt hour. And that's exactly what the utility company bills us in. Okay. So within that though, it's very rare to actually get a nice flat rate in terms of what they bill us for. There's different times of demand where we have to worry about what's going on in there. So it could be, say, during the middle of the summer, we might be paying a higher rate because more electricity is being used by everyone to run all their air conditioning. Okay. Different ways we can deal with that are things like demand limiting. We can actually shut things off when we're not in a room. Example being like turning off the lights. We can do load shedding where we actually turn off non-essential equipment and appliances to maintain a uniform load. So you can think about the fact of maybe using ceiling fans or box fans in your home with open windows versus switching over to having the air conditioning unit on at the early start of the summer. Then you can also do load shifting, which is actually taking any of our high energy usage loads and actually shifting those off at times of less demand. So examples might be having the dishwasher, the dryer, or the clothes washer, running those at night versus in the middle of the day when everybody else also has all of their air conditioning units running as well. Okay. Time of use rates, this is another thing that we can look at. Um, in here, if you look down here at the bottom as our example, here I'm going to make that a little bit bigger as we talk about it. So you can see here, during the summer peak from June 1st to September 30th from 1 to 7 p.m., so the hottest time of the day, you can see that for a single family, they're actually charging over 23 cents per kilowatt hour. But during the off-peak hours of 7 p.m. all the way up until just before 1 p.m. the next day, they're only charging about 7.5 cents per kilowatt hour. That's a heck of a difference. That's 3 times difference what we're paying during the hottest part of the day. Kind of gives you an idea to why we would do something like load shifting. And then we can see during the remainder of the year, we're only going to be paying about 7.1 cents per kilowatt hour, which is still cheaper than any of the other times during the year. Now, sometimes this might get even more complicated in terms of it's shifting for what is your what would be. So this is just residential. So commercial would have a different one. Industrial would have a different one as well. If you had an area that had high energy usage both in the summer and winter, we might actually see a summer peak. We might also see a winter peak if you're using a lot of electrical for heat. Okay. All right, we survived the majority of the chapter here, guys. Let's get into the last little part of it. This is where it kind of gets a little fun now. So first off, on the left, this is an electrician's wheel. I hate this thing. Let's make it a little more simplified, okay? Over here on the right, this is the example that I went over in class. Here's power, voltage, current, resistance. These are our 4 units that we talk about. Up here at the top, we have our 2 types of circuits. We've got a series circuit and a parallel circuit. So let's go over some of those rules real quick. Let's see. I know that in a series circuit, voltage is the sum of all the parts, meaning all the different parts around the circuit are equal to the source. And we know that current is constant. I use this little double-headed arrow to help describe that. Power works the same as voltage. We just sum everything up and it's equal to the power at the source. Resistance works the exact same way. Now in parallel, voltage and current are going to flip. In parallel, voltage is constant, but current is what we add up. And then power sums up the exact same way it did in series. Now the parallel, that's a little bit weird for how its resistance works, is we add up the inverses of all the resistances and then we do an inverse of that sum. And I'll go over this a little bit more as we go through one of the examples. Now on the far left over here, here's the other part. If we remember our first law, remember Ohm's law? Remember that current times resistance equals voltage. So in my little chart, if I'm moving upward, I'm going to multiply. And we can verify that current times voltage, yes, that equals power. If I'm going down in the chart at any point, I know that I need to divide. So if I know power and voltage, I divide power by voltage, that gives me current. If I divide power by current, I'm going down still, I can solve for voltage. If I know voltage and current, voltage divided by current gives me resistance. Voltage divided by resistance gives me the current. Here I've gotten it written out a little bit more for you, and I've got examples of the 2 types of circuits drawn up here for you as well. So let's go through an example of a series circuit here real quick. So on the left, I have a 12-volt power source. We've got 2 pieces of equipment in here using power. One has 10 ohms of resistance. The other one has 2 ohms of resistance. So I'm going to try and draw on here real quick and see if I can do this clearly. So maybe I'm going to have to do it on this slide. Sorry guys, trying to figure this out here real quick. So I know that I have a total, I have a component 1, and a component 2. So there's 1, there's 2, and this is what we're going to call total, okay? On the left here, I have power, I have voltage, I have current, I'll try and make an eye as best I can, and I've got resistance, okay? Let's see if I can draw straight lines in here. Better than I do on the whiteboard. Watch, I'm going to say that, then I'm going to mess up here. Okay, so what do we know? Well, we know that this is 12. Okay, so we know voltage at the source, the T, is going to be 12. I know resistance at 1 and 2, so resistance at 1 is 10. Sorry for my poor writing, guys. I don't have a stylus here. And resistance at 2 is 2. Okay? So these are our knowns. Let me see if I can switch over to a different color now. And hopefully this will work. Okay, so all this is just algebra. And we can do this. So what we're going to do is look for two things we know for what we can solve. So the first thing we remember is, I don't know current, so I can't write it in yet. Can't do anything with voltage. But I do know two of my resistances in a total. So therefore, I could add these two together to get the final total. So you can see that right here. 10 plus 2 gives us 12 ohms. Okay. Now I could solve for current because I know the voltage and the resistance of the total. So therefore, 12 divided by 12 gives me 1. Current is constant. So therefore, current here is 1, and current here is 1. We can now go back up. I want to solve for this voltage. I'm going up in my chart, so I take 10 times 1. That gives me 10. 1 times 2, that gives me 2. And here's the nice thing about this chart. It lets us check ourselves. I know voltage should be a sum, so therefore 10 plus 2 gives me 12. We did that right. If we want to go up and do our power, it's the same thing. Multiply up. 1 times 10 is 10. 1 times 2 is 2. Not a great 2, sorry. Add those together. That gives me 12. 12 watts divided by 12 volts gives me 1 amp. That is correct. We've just proven that, and we've solved for this problem. Okay? Let's go on to the next one and see what we can do. Oh, now we've got a parallel one. All right, this is going to be a little tougher to draw because they took away some of my area here. So let me go back to red. Come on. All right, so here I still have total. I have 1, and I have 2. There's my values. Not too much has changed. Okay, so in my table, I have total, 1 and 2, power, voltage, current. Well, hold on a second. Make those a little smaller. Sorry about that. Power, voltage, current, and resistance. Okay, apparently I can draw horizontal lines a whole lot better. Okay, so what do we know? Well, again, we know that voltage is 12. We know that the resistance of 1 and 2 are 10 and 20, respectively. Okay, so now what can we solve for? Let's look at this. Well, I could do the nasty math and actually do this. But if we remember one of our rules, remember voltage here is constant, I could actually carry this voltage over. So therefore this is 12 and this is 12, as poorly as I draw with my mouse. We could then go down. 12 divided by 10 is 1.2. 12 divided by 20, 0.6. All right. Let's add these together. 1.2 plus 0.6 gives me 1.8. All right. And if I take 12 divided by 1.8, that is going to give me 6.67. Now if I go back and do all that nasty math right here, you can see that that actually gives me that 6.67. Okay. If we wanted, we could go up. Power works the exact same way. So let me grab a calculator here on my side. Okay. So if I had 12 times 0.6, that would actually be 7.2. I could have 12 times 1.2. That's 14.4. And if I add those two together, I'd get 21.6. And if I divided that by the 12 volts, I'd still get my 1.8. So you can see that the table helps us check all of our work, but that's a parallel circuit and that's pretty easy, okay? So you can see series and parallel aren't all that hard. You just take your time as you work through them. Now, unfortunately, the world is not made up only of series and parallel circuits. We also have combination circuits. Now, this is where we intermix series and parallel as well. Okay, so let's look at this combination circuit here. So all we have to do now is we have to figure out how do we simplify this down to just either a basic series or a basic parallel circuit. So let's take a look at how to do that real quick. So again, I've got my pen going. So let's see, let's do this right here. It's going to be a little smaller. I apologize for that. You'll be able to zoom in on your screen, I think, if you need to. But in this case, we're going to have our total, 1, 2, and 3. So watch what I'm going to do. I'm going to say total, 1, combination of 2 and 3, 2, and then 3. Over here we have power, we have voltage, current, and resistance. Now I'm going to zoom in so it's a little easier to write on this, okay? No, it's not going to let me. Evil slides. All right, I'm going to do my best here. In the future, I'm going to have to add a blank slide here. Oh, that's going to be tough. I don't have a text tool, do I? All right, do the best I can here. Okay, so what do we know? We know that the voltage at the source is 12. And we know that the resistance at 1 is 10. We know that the resistance here is 20. We know that resistance here is 40. It's a little tough to read. That's why I've got it written out right here for you, okay? So what we're going to see here is that this is all the stuff we know. We're kind of looking at going like, well, what the hell am I going to do? Well, what we're going to do is we're going to try and take this part right here and convert it, simplify this into another little series component. So what we'll end up with, I'll draw this real quickly, over and back, is that this part right here is what we're going to convert that into. Sorry for the poor level. If we were on the real whiteboard, this would be a lot easier. Okay. So let's see. What we'll do here is we're actually going to say, well, let's figure out how we treat this circuit. So this portion of right here, so our source, our 1, and then this is that 2, 3 that we're making these into. All of that, that's in series, okay? This portion right here, the 2, 3 through the 2 and 3, that's actually in parallel. And that allows us to solve this. So if we think about it, if we just ignore these two columns right here, so just the 2 over 3, the 2 and the 3, this is like its own little parallel circuit. We're going to combine those together. So because this is a little bit of nasty math to do the 20 and the 40, I have it right here on the side. Okay? So here's the 1 over the 20 plus 1 over 40. And then the inverse of those gives us 13.3. We'll call that good. I know it's 2 decimal places here. This is good enough for my little bitty chart for my very, very bad writing. Okay? So we can think of it that way. Now, if we look at just the series portion, so total 1 and 2, 3, I've got 2 sets of resistance and a total. I can add those together to get this part right here. Okay? And that's going to give me 23.3. Kind of sort of there. Again, sorry for this. I will go over these in class again as well. As we go through now we can actually start doing the math. So we can see that now I know resistance, I know voltage. I can solve for my current, which is going to be 0.51. 12 divided by 23.3. I know that in the series portion, my current is constant, so this is also 0.51, as is this. Okay? We can now go up and do voltage. So 10 times 0.51 gives me 5.1. Okay. We can, if I want, I can now subtract this, and I get 12 minus 5.9 gives me 6. Yep, that was pretty bad. 6s are not easy with a mouse. I could actually have 6.9. Now, if I did the actual math going up here, and I did 13.3 times 0.51, I actually get 6.78. Now, this is where we get into the issue of rounding error. So you can see right here, there's the first one we made, because really this has a whole bunch of 3's following it. Okay? So, and the same here, this isn't exactly 5.1, 23.3, hold on, sorry, 12 divided by 23.3 is actually 0.51502.145. A whole bunch of stuff going on in there. So you can see we also have a rounding error there. Those rounding errors start to compound. That's why this number isn't exactly exact. However, for us, if you're within plus or minus 1 or 2 on point, if you're within plus or minus point, let's say 1 or 2, you're probably pretty good, and you can get pretty close to what you're doing here, okay? Now let's continue on. So if I look now in the parallel portion, I know voltage, I know current. I know this is going to be constant, so this is going to be 6.9. That is a horrid 6 and a 9. This is going to be 6.9. If anybody knows a better way to draw on these slides, let me know. I've got those two. Now I could do the math going down. This gives me 0.35. Going down here, this will be 0.17. If I add those two together, I get 0.52. Again, our rounding errors, so therefore close enough for what we're trying to get out of this. Okay? Power works the same way. Multiply these two up. So 6.9 times 0.35 gives me 2.4. I've got 0.17 times 6.9 gives me 1.2, and I am rounding a bit here, guys. Okay, add those together, that gives me 3.6, and if I did 0.51 times 6.9, I get 3.519. So you can see we're within plus or minus 0.1 there. Okay, so again, when I'm doing the parallel portion, I'm only staying within these columns. When I'm doing series, I'll only be there. So let's do those real quick. 5.1 times 0.51, 2.6. If I add 2.6 plus 3.6, I get 6.2. Which if I take that divided by 12, I actually get 0.51, but with a 6 repeating, so closer to 0.52. But you can see that within that chart, we're actually able to check all of our work and still do all the math, okay? So here's a few little tips and tricks that help us to get through this a little more easily. First up, if I have two loads in series with the same, that are the exact same, so let's say I have two 10 ohm resistance loads, I can actually say that all I have to do is split the voltage. So if it was two 10 ohm resistances and I had a 12 volt battery powering it, each one of those would be 6 volts across them, okay? If I have two loads in parallel, they split the current. So exact same. In series, you could split the voltage between similar loads. In parallel, you split the current. When you have multiple different loads in parallel, the total parallel resistance will be smaller than the smallest. Let's go back for just a second. So here you can see that. Here's 10 and 20 in parallel, and our total resistance in parallel was 6.67. It's smaller than the smallest of the loads. Okay? We also see that current takes the path of least resistance, so the smaller the value of parallel resistance will always carry more current. Let's go back again. So if we look here, here's 10 ohms of resistance and 20 ohms of resistance. This is the smaller resistance, therefore you can see it's carrying more current than the other one. Okay? All right. And that's actually the end of the slides for this chapter. I will go back over parallel, series, and combination circuits in class one more time. And additionally, I will go over the math as well. I think I may actually do a real quick video here again, if I have the time, over the math to let you be able to get a start on that. I'll just open it up and I'll just do a real quick example of it here on the screen, okay? All right, hopefully everybody's doing okay with their work, and I will see you all in class next time. Have a great day. Bye.